Hello friends. So today we are going to solve the questions from modern physics, and these questions are from the year 2023. So total 11 questions we are going to solve today, and all these 11 questions are from mains. And for the year 2023, this is part 3. The first question, it states that assume that protons and neutrons have equal masses. Mass of nucleon is 1.6 into 10 to the power minus 27 kg, and radius of nucleus is 1.5 into 10 to the power minus 15. The approximate ratio of nuclear density and water density is n into 10 to the power 13. The value of n is. So here we are given that mass of the nucleus is given to us. So we are given mass of nucleon, and that is given as 1.6 into 10 to the power minus 27 kg, and its radius is also given. Radius is given as 1.5 into 10 to the power minus 15, 1/3 meters. And we have to find out the ratio of nuclear density to water density. Approximate value of nuclear density we already know. Sorry, not nuclear density but water density. So you can say density of water is, let us suppose, rho water, and that is approximately as about 10 to the power 3 kg per meter cube. And we are supposed to find out the nuclear density and then take their ratio. So we can say that our nuclear density let us suppose that is given as rho nuclear will be equal to our mass of the nucleus divided by volume of the nucleus. Mass of nucleus, volume of nucleus. And if we assume that the nucleus is having a mass number A, and from there we can find out the total mass. So we say that our mass number is suppose A, and mass of each nucleon, mass of each nucleon is, let us suppose, small m. So from here we can find out the total mass. We can say our total mass will be equal to mass number multiplied by mass of each nucleus. And let us suppose this is represented as capital M. And we can also write the formula for our radius in terms of mass number. So we can say radius, that is a capital R, will be equal to our R naught a raised to power 1 by 3. And this R naught is our constant value, and its value is our 1.5 into 10 to the power minus 15 meters. And based on this radius R, we can easily write the equation or formula for volume. Therefore, we can say volume of nucleus that is a V will be equal to 4 by 3 pi r cube, and we substitute the radius, we get this as 4 by 3, and this is a pi r naught cube multiplied by a. Now we got both mass of the nucleus and volume of the nucleus. Therefore, we can write our nuclear density, rho nucleus will be equal to number multiplied by mass of nucleon, and here we have 4 by 3 pi r naught cube multiplied by mass number, that is our A. Total, mass number. So this A and A cancels out. So we get this as, we can just substitute the values. We are given that mass of nucleon is 1.6 into 10 to the power 27 minus 27, 1.6 10 to the power minus 27, 4 by 3, and this is a pi 1.5 into 10 to the power minus 15, and this comes as whole cube. And we get that our density of the nucleus will be approximately equal to 1.132 into 10 to the power 14. Now we can just substitute the, you can say, find out the ratio which we are required to ultimately solve for. Therefore, you can say ratio, we have density of nucleus, density of water. So this comes as 1.132 into 10 to the power 14, and this is our 10 to the power 3. So this ratio will be coming as 1.132 into 10 to the power 14, and we are given that this is equal to n into 10 to the power 13. So we can change the equation in terms of 13. So we can write this as 11.32 into 10 to the power 13. So 1:1 comparison gives us that the value of n is approximately equal to 11. Value of n is equal to 11. Next question. It states that a photon is emitted in transition from N4 to N1 level in a hydrogen atom. The corresponding wavelength for this transition is, given that the value of H is 4 into 10 to the power minus 15. And we are given the photon is emitted when the transition is from fourth level to first level. And during this transition we can find out the energy difference between the two levels, and from there we can use this energy level and relation with the wavelength and get our wavelength which is required. So we can say the energy difference that is our delta E, and we have transition from 4 to 1, therefore we can write our delta E will be equal to our E1 minus E4, and we also know that a relation for our nth level E of n is our minus 13.6 upon n square. So therefore we can write this as our this will be our 13.6, and this comes 1 minus 1 upon 4 square, and this will be equal to 13.6 into 15 by 16. So from here we get our delta E will be equal to 12.75 electron volt. Now we can just use the relationship between this energy as well as the wavelength. So we can say the photon energy wavelength relation, photon energy wavelength relation, which gives us that our E is equal to hc upon lambda, or in terms of this change in energy we can write lambda is equal to hc upon delta E. We can simply substitute the value. H is given as 4 into 10 to the power minus 15, and speed of light is our 3 into 10 to the power 8. Delta E we found out is 12.75, and this gives us that a lambda will be approximately equal to 9.41 into 10 to the power minus 8 meters. So okay, it's in nanometer, therefore we can write 94.1 nanometer. So 94.1, option 1 is correct. Correct. Next question. It states that the wavelength of a radiation emitted is lambda naught when an electron jumps from second excited state to the first excited state of a hydrogen atom. If the electron jumps from third excited state to the second orbit of the hydrogen atom, the wavelength of the radiation emitted will be 20 lambda naught divided by x. Then the value of x is. In this case, we are having, you can see, two different wavelengths for different excitation, two transitions. Okay. So in this case, the wavelength is our lambda naught when the transition is from second excited state to the first excited state. Therefore, we can say that our transition is from, first you have second excited state, which basically means value of n is equal to 3, and it jumps to first excited state, and which gives us value of n is equal to 2. And during this transition, the wavelength is given as lambda naught. Wavelength is our lambda naught, and we have a second transition which is from third excited state, which means value of n is equal to 4, and this is up to our second orbit. Second orbit, which basically means that the value of n is equal to 2. And in this case, the wavelength is given to us 20 lambda naught divided by x, and we are supposed to find out value of x. So we are going to use Rydberg formula for these two transitions. Okay. So we say Rydberg formula and that Rydberg formula is our 1 upon lambda is equal to r. We have 1 upon nf square minus 1 upon ni square. And we have two wavelengths. First wavelength is our lambda naught. Your first transition is our from 3 to 2. Therefore, we can write this as 1 upon lambda naught is equal to r 2 square minus 3 square, and this comes as our 5 upon 36 times r. And let us assume that for second wavelength, that wavelength we assume, let us suppose, is our lambda 1. Later on we can convert into this lambda naught. So we get this as 1 upon lambda 1 is equal to r, and this comes our 1 upon 2 square minus 1 upon 4 square, and this will be coming as 3 by 16 times r. And let's find out the ratio. So we can say our lambda 1 upon lambda naught, and our lambda 1 is our 3r upon 16, lambda naught is our 5r upon 36, and here r and r cancels out, so this comes as 3 upon 16 multiplied by 36 upon 5. One second. Sorry, my mistake. It should be reverse. This relationship will be, or can be written as 1 upon lambda naught and 1 upon lambda 1. I simply substitute the values directly. 1 upon lambda naught is our 5r upon 36, and 1 upon lambda is our 3 upon 16. Now this comes as 5 upon 36 multiplied by 16 upon 3. This gives us 20 upon 27. But we are given, or rather we can say we assumed, that our lambda 1 is our 20 lambda naught by x. Therefore, we can use that now. So lambda 1 is equal to 20x by lambda naught, and from here we can write lambda 1 upon lambda naught is equal to 20 upon x. This comes as our 20 upon 27. So this 1:1 comparison, this gives us that our value of x is equal to 27. So value of x is 27. Next question states that the energy levels of an atom as shown in the figure, which one of these transition will result in emission of a photon of wavelength 1 to 4.1 nanometer, given H is 6.6 into 10 raised to power, this should be 10 raised to power minus 34. And here we are given 4 levels. When there is a transition between 1 and 2, it is called as A, and between 1 and 3 it is called as B, between 2 and 3 it is called C, and D is called as between 1 and 4. So we are supposed to find out our wavelength, which is given to us, and it said that which transition will be resulting in the wavelength of 1 to 4.1. So in this case we are going to use the relationship between our change in energy and wavelength. So we can say energy and wavelength. We know that our lambda is equal to hc upon delta E, and delta E is our difference in energy between two transitions. So let us consider first of all our transition number A. Therefore we can write for A, the transition is from N1 to N2, and energy at 1 is given to us as 0, and energy at 2 is given as minus 2.2 electron volt. Therefore we can write that our delta EA will be equal to our E1 minus E2, which will be 0 minus of minus 2.2, giving us 2.2 electron volt. Similarly, we are going to solve for our B also. So we can see for B, we are having transition from N1 to N3, and energy at 1, that is our E1 is given to 0, and energy at level 3 is our minus 2 electron volt. So from here we can write that our delta EB will be equal to our E1 minus E3, which gives us 0 minus of minus 5.3, giving us 5.3 electron volt. Now let us deal for C. So if we can say for C, transition is from N2 to N3, and energy at 2, it is given to us as minus 2.2, and energy at is minus 5.2. So we can find out delta EC will be equal to E2 minus E3, and we get this as minus 2.2 minus of minus 5.2. So delta EC is equal to 3 electron volt. And finally is for our D. For D, the transition is from 0 to N1 and 0 and minus 10 volt. So E1 is 0. Sorry, 1 second. N1 to 4. Yeah, my mistake. It starts from 1 and end at 4. So E1 is 0 and we have E4 is equal to minus 10. Therefore from here we can find out our delta ED, which will be equal to our E1 minus E4, giving us 0, 0, 10. So therefore delta ED will be equal to 10 electron volt. Now we got all the difference energy. Now we can just find out our wavelength for each part. So let us start for A. That is our delta of A will be equal to HC, that is 6.6 into 10 to the power minus 34 into 3 into 10 to the power 8, and delta EA is our 2.2, and 1.6 into 10 to the power minus 19 joules. Oh, sorry, converted into joules the energy because it was electron volt, and this will be giving us approximately as 564 nanometer. Now for our delta B will be equal to our numerator will be our product of HC, that is 12.41, and this is our 5.2. This will be giving us 238.65 nanometer. Lambda C is equal to 1241 divided by 3. This will be giving us 413.66 nanometer. And finally is our D. Lambda D is equal to 1241 divided by 10. This will be obviously giving us 14 nanometer. So therefore option number D is correct. Option 4 is correct rather. Option 4 is correct. Next question. It states that the speed of electron in Bohr's 7th orbit for hydrogen atom is 3 into 10 to the power 6 meter per second. The corresponding speed of electron in the 3rd orbit in meter per second is. So this is directly based on the formula, and we know that the speed for the nth orbit in the Bohr model, the relationship we already know, and we can write that electron speed in nth orbit, that is our V of n, is equal to V of 1 upon n. Here this V of 1 is speed in first orbit, speed in first orbit. Or from here also we can write in terms of proportionality that V of n is proportional to 1 upon n. So we can divide this proportionality into two parts. First is our 7th orbit and second is our 3rd orbit. Therefore we can write that our V of 7 is proportional to 1 upon 7 and V of 3 is proportional to 1 upon 3. So let us take this ratio. From here we get our V7 upon V3 will be equal to 3 upon 7. And V7 is given to us, we need to find out V3. Therefore we can say our V3 will be equal to V7 multiplied by 7 by 3. And this is our 3.6 into 10 to the power 6 multiplied by 7 divided by 3. And this will be coming as, it goes by 1.2, and therefore this will be equal to 8.4 into 10 to the power 6 meter per second. So option number 4 is correct. Next question. It states that for a hydrogen atom, lambda 1 and lambda 2 are the wavelengths corresponding to the transition 1 and 2 respectively, as shown in the figure. The ratio of lambda 1 to lambda 2 is x by 32. The value of x is. So we are having two transitions. Transition 1 is from n3 to n1, and we are having transition 2 which is from 2 to 1. So we have two transitions and we have our wavelength lambda 1. Therefore we can say that we are having transition n3 to n1. This is called as a first transition and the wavelength is our lambda 1, and we have our n2 to n1. This is called as a second transition and the corresponding wavelength is lambda 2. And here we are going to use the Rydberg formula to find out the ratio. So we can say our Rydberg formula, which gives us 1 upon lambda is equal to r z square 1 upon n1 square minus 1 upon n2 square. So we have two wavelengths, so therefore we can divide this formula into two parts. 1 upon lambda 1 is equal to r z square, we have 1 square minus 1 upon 3 square. This will be giving us r z square multiplied by 8 by 9. Second wavelength is our lambda 2, so same formula r z square, and the transition is from 2 to 1. So this is 1 square minus 1 upon 2 square, which gives us r z square multiplied by 3 by 4. And we take the ratio. Ratio is for lambda 1 by lambda 2. that is, so you can write this as our lambda 1 upon lambda 2. Let me, lambda 1 will be our 9/8 RZ square, and lambda 2 will be 4/3 and RZ square. So here RZ and RZ square cancels out. So this comes as our 9/8 multiplied by 4, and this comes as 3. So this will be equal to 27 upon 32. But this ratio is given to us x upon 32. So this gives us that the value of x is equal to 27. So value of x is 27. Next question. It states that if the binding energy of the electron in a hydrogen atom is 13.6 electron volt, the energy required to remove the electron from the second excited state of lithium 2 positive will be x into 10 to the power minus 1 electron volt. The value of x is. And in this case, we are given binding energy of the hydrogen, but finally we have to calculate it with respect to lithium 2 positive ion. Okay. And lithium 2 positive is a hydrogen like atom, but with different value of Z. Okay. So we are given that our binding energy of hydrogen atom, and the value of Z in this case will be equal to 1, and this binding energy is given as 30.6 electron volt. And we have lithium 2 positive, and this is our hydrogen like atom. Hydrogen like atom, but the value of Z is equal to 3. And it states that electron from second excited state. Okay. So second excited state means value of N is equal to 3. Second excited state means that the value of N is equal to 3. And we are supposed to find out energy required to remove from the second excited state. So basically in this case it is asking about the ionization energy. Ionization energy. And so we are going to use our you can say basic formula, energy at nth level, and from there we can just calculate our ionization energy. So we can say energy at nth level, that is E of n, is equal to minus 13.6 multiplied by Z square and divided by N square. And value of Z and N is same in this case. Therefore, we can say our E of 3 will be equal to minus 13.6. This comes as our 3 square as well as our 3 square, giving us that our E of 3 is minus 13.6 electron volt. And we are going to find out for ionization energy. we can say our ionization energy will be our E of 3 and its modulus. Okay, so this gives us 13.6 electron volt, and in the question it is given as x into 10 to the power minus 11, so we can just write it as 136 into 10 to the power minus 1, not 11, and given equal to x, given equal to x into 10 to the power minus 1. So 1:1 comparison gives us that the value of x is equal to 136. Value of x is 136. Next question. It states that the masses of a neutron and proton are 1.087 and 1.0073 AMU respectively. If neutrons and protons combine to form a helium nucleus of mass 4.0015 AMU, the binding energy of the helium nucleus will be. So here we are going to find out first of all the total mass, and then we are going to compare it with the actual total mass of the helium which is given to us, and from there we are going to find out the mass defect, and that will be resulting finally into us our binding energy. Okay. And it says that it forms a helium nucleus. So in the formation of our helium nucleus, it contains 2 protons and 2 neutrons. So we can say our helium nucleus it contains 2 protons and 2 neutrons, and mass of 1 proton and 1 neutron is given to us. Therefore we can say that our total mass will be equal to 2 multiplied by mass of 1 proton plus mass of 1 proton and 2 multiplied by mass of 1 neutron. And let us suppose this total mass is given as capital M, or rather M1 we say it, and we substitute the value, we get our M1 is equal to 2 times 1.073 plus 2 times 1.0087, and this comes as 4.0320 AMU, and the mass of helium nucleus is given to us as 4.0015. So we can say mass of helium nucleus, given mass of helium nucleus let us suppose we call this as M2, that is given to us as 4.0015 AMU. Now we can use our mass defect. That is our delta M will be equal to our M1 minus M2, which gives us 4.0320 minus 4.0015, and this will be coming as our point, this will be our 5 0 yeah 3, and this will be 0 AMU. Now we can just convert this into energy. That will be our binding energy. So we can say our binding energy will be equal to our delta M multiplied by 931, which gives us, because 1 AMU is equal to 931 mega electron volt. So this comes as 0.0305 into 931 mega electron volt. So finally we get this will be equal to 2842 mega electron volt. So 28, option number B is correct. Option B is correct. Next question. It states that light of energy 12.75 electron volt is incident on a hydrogen atom in its ground state. The atom absorbs the radiation and reaches to one of its excited states. The angular momentum of the atom in the excited state is x upon pi into 10 to the minus 17. The value of x is, use h and c is given to us. So in this case, we are given that photon energy is given to us. So we can say incident photon energy, that is our E, and that is given as 12.75 electron volt, and it states that incident on its ground state. So ground state energy we already know. So we can say that ground state energy of the hydrogen atom ground state energy of hydrogen atom, that is our E of 1, is minus 13.6 electron volt, and it says that it jumps to a different level. Okay. So it means the ground state, the electron is already having this much energy, and the energy it is going to gain from the photon will be equal to 12.75. So from there we can find out the final energy of the absorbed final energy. So we can say our energy absorbed, or let's write it final energy. Final energy, that is a E of F, will be equal to our E1 plus the energy of the photon, and E1 is minus 13.6 plus 12.75 electron volt. Therefore we get that our final energy will be equal to minus of 0.85 electron volt. Now we can use our energy level and find out the value of n, to which level it can maximum go based on the energy. Okay. And we can say energy for the nth level, energy for nth level, that is E of n, is minus 13.6 upon n square. and the energy corresponding to nth level will be our this final energy, which will be with the excited part. So therefore we can write that our minus 0.85 is equal to minus 13.6 upon n square. So we get our n square is equal to minus 13.6 upon 0.85, and this is minus. So we get our n square is equal to 16, value of n is equal to 4. So it means the maximum level up till which it can, or we can say the excited state, maximum excited state will be equal to n is equal to 4. And it states that in the question it mentioned that the angular momentum at this state is x upon pi into 10 to the power minus 17. So now we can use the formula for the angular momentum. Angular momentum in Bohr model, let us suppose that L is equal to n h upon 2 pi. N we already know is about 4, so this becomes as 4, and h is 4.14 into 10 to the power minus 13 upon 2 pi, and this comes as 8 to 8 into 10 to the power minus 17 2 pi, and in the question it is given as x upon pi. So we can write this is equal to x upon pi into 10 to the power minus 17. X upon pi, x upon 2 pi. Sorry, this is x upon pi, my mistake. Yeah, and therefore this 1:1 comparison gives us that the value of x is 8 to 8. Next question. It states that an electron of hydrogen-like atom having Z is equal to 4 jumps from fourth energy state to second energy state. The energy released in this process will be. Okay, so we are simply going to find our amount of energy released when there is a transition from fourth energy state to second energy state. And so we are given that the transition is from fourth energy state so it means this will be our initial, that is our n1 will be 4 and 2, and it is second energy state, which gives us a final, that is of n2 is equal to 2. So we can use the direct formula for energy difference in terms of the states. We can say energy difference and or we can just, let me write the formula here. We know that our E of n is equal to minus 13.6. Energy for our nth level E of n is equal to minus 13.6 z square upon n square. So energy difference will be our delta of E, and that delta of E can be written as our E2 minus E4. So we can just plug in the values. We get our delta of E is equal to, and we are going to have this minus 13.6. Z is given to us as 4, so this comes as 4 square, it will be common. This comes as 1 upon 2 square minus 1 upon our 4 square. And this will be equal to our one second. Okay, let me reformulate it positive, otherwise this will be giving us a negative. Okay, so it should be E4 minus E2 actually, but anyway, it doesn't matter. This minus can be sorted out quite easily. So this gives us 13.6 multiplied by 16 multiplied by, this will be coming as 3.16. Yeah, 3.16. So therefore we can say our delta E will be approximately equal to 40.8 electron volt. So this is option number 4 is correct. Four is correct. Next question. It states that nucleus A having Z equals 17 and equal number of protons and neutrons has 1.2 mega electron volt binding energy per nucleon. Another nucleus B of Z12 has total 26 nucleons and 1.8 mega electron volt binding energy per nucleon. The difference in the binding energy of B and A will be. Okay. So in this case, we have two nucleus A and B, and they are having different energy as well as different combination of nucleons. Okay, let's start with A. We can say our nucleus A for nucleus A, we are given that our Z is equal to 17, and it also states that number of protons equal to number of neutrons. Number of protons equal to number of neutrons, and therefore we can say that our number of neutrons will be equal to 17. So we can write from here total nucleons. Total nucleons will be equal to number of protons plus number of neutrons, that is our 17 plus 17 is equal to 34, and we are given binding energy per nucleon is given to us, so we can find out a total binding energy of A. We can say total binding energy of A, let us call this as BAA will be equal to total nucleons 34, per nucleon is given as 1.2. So this will be giving us 40.8 mega electron volt. Same calculation we can do for our nucleus B also. Nucleus B, value of Z is given as 12 and total nucleons is 26. Value of Z is given as 12 and total nucleons is given to us as 26. Therefore, total binding energy of B, total binding energy of B will be is equal to 26 multiplied by per nucleon, that is 1.8, giving us 46.8 mega electron volt. And we have to find the difference in binding energy. So we can say that difference in binding energy will be equal to binding energy of B minus binding energy of A, which gives us 46.8 minus 40.8. Therefore, difference in binding energy delta BE will be equal to 6 mega electron volt. That was asked for, that is equal to our 6 mega electron volt. So this completes part 3 for the year 2023. In this part 3 we solved 11 questions, and all these 11 questions were from mains 2023 only. So this completes part 3 of year 2023. Thank you.